Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Thank you, Anna. Hello, everyone. Good morning, good afternoon, and good evening from me as well. I am Guilherme Martinez Roura from the International Telecommunication Union, and I would like to welcome you all for joining today's AI for Good event on soft robots for humanity, organized by the ITU. Today's session will delve into robotic systems and haptic devices that combine softness and rigidity to achieve the best of both worlds, enabling novel shape control, generating significant interaction forces, and providing a compliant interface. These soft robots integrate with physical and artificial intelligence, making a significant impact on the Sustainable Development Goals. This session is part of the AI and Robotics Discovery Series, which features expert talks on the state-of-the-art developments in autonomous robotic systems to advance the United Nations Sustainable Development Goals. We have a very distinguished speaker today, but as always, we're counting on you, the participants, to help create a very interactive session. As a reminder, the audience can leave questions in the AI for Good neural network chat room that will be answered during the Q&A section. So without further ado, I would like to introduce our distinguished speaker today. Her name is Professor Alison Okamura, and she's the Wayland Professor of Engineering at Stanford University. Alison, the floor is yours. Thank you.
Thank you so much for having me. It's an honor to be here. I'm just going to share my slides. All right, I'm excited to be here today to talk to you all about soft robots for humanity. Soft robotics has been a growing area or subfield of robotics over the last 10 to 15 years. And it's an exciting way to think about the interaction between AI and physical embodiment. So the field of soft robotics, as I mentioned, has been growing in the recent decades. The idea, though, of soft robotics is quite general. You can have a whole continuum of robots that are partially soft to entirely soft. And if you're interested in seeing some of the background of the field, one of the earlier review articles that's very complete is from 2016, which talks about primarily bio-inspired robots, ranging from those that are mostly stiff with a few compliant elements to ones that are entirely soft, even including some of the computation effectively happening through chemical interactions. So an important note is that the different soft robots, especially the ones featured here, some of them are very soft because they are using elastomeric materials, and the materials are inherently very stretchy or flexible. But you can also be soft based on structure. You can have some materials that in some form factors might be very hard, but then if they're distributed in a particular way, the structure can enable the whole thing to be relatively soft. And another important note is that all soft materials are not the same. Some are flexible in that they can bend, and then some are stretchable in that they can stretch. And depending on how they're structured, you can get certain properties. And the benefits of soft robots for humanity primarily include adaptability, as was mentioned in the intro, We have soft robots that can conform and adapt to the human body, for example. Safety, they tend to have relatively low inertia and low contact stiffness, which can be safe for both human interaction as well as interaction with delicate environments. And what can be, but not always true, is that soft robots can be less expensive than some traditional systems. They can be manufactured or fabricated, often without a fancy infrastructure, and this can actually make them more accessible to different communities. So the way, there's so many different types of soft robots. So I think a way to guide you through some possibilities in the field is to give a few examples from my own research lab. So I'm going to talk a little bit in the beginning about patient-specific medical robots, which was my foray into this field. Spend a lot of time talking about robots that grow by tip aversion, also known as vine robots, and then end with some examples of soft wearable haptic devices to really spark your imagination about how these robots interact with the human body. Now, in many of these scenarios, the field of soft robotics is based on a long history of work in continuum robots. So these are robots that aren't consisting of discrete joints and rigid links, but rather robots that have near infinite degrees of freedom. And a lot of these early robots were not really termed soft robots, but now they're recognized as such. And some of the challenges in making these soft robots function well is getting the right materials, having them be able to achieve these sort of continuum shapes, but still be able to apply strong forces to the environment. Because of course, a goal of robotics is to apply forces to the world in order to do good. And so if the robot is too soft, then it can't actually interact with the environment in a useful way. We have to be able to control the tip of the robot as well as its overall body shape. And then there are some technical challenges related to how do you model them? How do you design them and optimize those designs? How do you integrate sensors? And overall, in order to do a task in the world, you have to understand how to exploit the environmental interactions. So these are examples of a number of concepts behind continuum robots. And I think it's also important to note that many of these soft robots are based on biological inspiration. And since several of the systems that I'll describe to you today are built on the concept of growth, I thought I'd give some bio-inspired ideas that are related to growth. So pollen tubes, for example, grow over time, of course, relatively slowly. Nerve cells in animals also grow. And I mentioned one of our robots is called the vine robot, and that's inspired by the growth of vines, which can not only access places that are difficult for humans to go, but also stay in place in situ for long periods of time, which could have advantages. So biological inspiration for growth has driven a number of the projects I'll talk about. So the first project I'd like to highlight is related to medical robotics. So when you think about robotics that help people, I think medical robotics often come first to mind. And the idea behind soft robots here is being able to create structures that can go into the body in the least invasive fashion possible. So in this example, which is concentric tube robots, which I'd say we developed before I think the term soft robotics was really even thought of as a subfield, the idea is that we used semi-soft materials, in this case nitinol, which we use for its super elastic properties, and we make them into pre-shaped tubes. And those pre-shaped tubes, if you insert and spin them relative to each other, result in changing shapes and this sort of tentacle-like behavior. And the reason why this is so useful for medical robotics is that unlike robots that have to have transmission through cables or even motors placed right at joints, all of the actuation, the motors can be outside the body, allowing for this very tiny entry into the body. You can see that the tip here is only 0.8 millimeters. Now, in contrast, let me give you an example of what is used currently in surgery today. And by the way, if you're the squeamish type, this is all artificial tissue. That is rubber and foam, not actual tissues. And this is a really amazing robot, the Da Vinci surgical system, which is a teleoperated surgical robot. And it does have lots of advantages. You have a human operator, as shown at the bottom, manipulating these fancy joysticks. And then the robot on the patient side, which is shown at the top of the split screen, is following the movements of the surgeon's hands through a teleoperation control lock. Now, the patient side robot that you see in this case at the top of the split screen is magnified almost 10 times over what you see in the lower screen. So by teleoperating the surgical robot, it shrinks the surgeon down and makes them more effective. However, one of the challenges is that these instruments are long and thin, and the ones that are mostly clinically available today are very rigid. And that means you can't actually access everywhere you would want to in the body. So the idea behind using these concentric tube robots is they can be skinnier, therefore have less invasive access. And instead of also being straight with a wrist at the tip, like you saw in the previous video, the whole robot shape can curve. And this is some example work that was done by my former PhD student, Tanya Morimoto, who is now on the faculty at UC San Diego. And it shows an example of how we can design patient-specific robots that are just right for a particular person. So we begin with CT scans of a particular patient, in this case a pediatric patient whose body is relatively small compared to an adult. You get a 3D model, and then you can create either an optimization to design the robot autonomously, but you can also have a human in the loop. And so what's shown here on the bottom left is a design phase where a surgeon can be manipulating the robot, a virtual version of the robot in a virtual environment representing the patient, as shown in this video at the top. And as they do that, they themselves can be in the design loop to help create the right robot that's just in the right shape for that particular patient. And as an aside, I think an interesting thing about as you put more technology into the operating room for a surgeon, it used to be in the old days that surgeons would often design some of their own instruments and be able to actually change the technology they were working with in order to be just right for a particular patient. But as these systems become more complex, then it becomes more difficult for a surgeon to actually be part of the design process. And I think what's exciting about this project is that the surgeon can actually be in the loop in the design. In any case, the next step is once the design has been completed and approved by the surgeon, you can fabricate, in this case 3D print, these tubes, and you can attach them to a base robot in order to provide more degrees of freedom and actually perform the task. And I thought I'd just highlight a little bit the 3D printing process. 3D printing, of course, is an amazing technology which allows us to rapidly fabricate robots. I think it used to be considered really just a prototyping technology, but now, of course, you can make 3D printed structures that are used in practice. And in fact, some of these materials are biocompatible and actually are very safe to place in the human body. So here's a very simple example of printing some relatively flexible tubes in order to create one of these concentric tube robots to go inside the human body. And you can also even make the drive mechanisms themselves more compact by integrating novel gear mechanisms and be able to create a lightweight system that you can place on another robot or even hold in the human hand in order to provide this minimally invasive access. So I mentioned before that these robots grow in a way, and they do. They telescope in and out, and that allows you to get this minimally invasive access, right? To get deep into the body without having to slide the whole instrument inside. We have new material come from the tip, and in this method, we use this telescoping method. But there is another way to grow, and that is of the form that we use in our Vine robots. The idea here with this very different type of robot is that still has this long, skinny form factor, is that we have a membrane. It could be fabric, it could be plastic, as shown here. And as you create it into a tube, you can also flip that tube inside such that you have more material on the inside. And then when you apply pressure to it, the tip turns inside out, also known as eversion, and that allows it to grow. And so this video here just shows a close-up of what it looks like at the tip, showing that new material comes from the tip and turns inside out, unwrinkling and causing growth. And then that process can be reversed in order to retract the robot as well. And a lot of the work I mentioned here was spearheaded by Elliot Hawks, former postdoc who's now at UC Santa Barbara. And I'm going to spend the majority of this talk discussing these Vine robots because there's so many interesting applications for these robots that are relevant to UN Sustainable Goals. So let's look at what this type of robot can do and what is its basic structure. So one of the great things about this type of system is that when you use pneumatics, you can use air, which is a readily accessible filler material, in order to make the robot extremely long. And so in this case, we have a spool of simply LDPE tubing, so that's low density polyethylene tubing, similar to the kind you get when your materials are packaged in when you purchase something, and that's makes a very compact base. And then when you take that tube out and you flip it inside out and you fix it, you have this closed air in this light gray area here, and then you can have a compressor or other type of pump and apply air inside, and then the air itself pushes the robot to extend its length and to evert. And it's important here that the material be flexible, that is, it can bend, but it can't be stretchable, because if it was too stretchable, then it would expand in diameter rather than extending its length and everting. And so in these examples here, you can see, I think I'm just going to go back so I can restart the videos. We see an example of a relatively small spool of tube you can see on the lower left. And when that tube is expanded, it grows about the length of a football field. And in this case, we're not actually actively steering it. We just grew it and it sort of bounced off of its environment. And you can see you can also grow against gravity if desired. So you can get this very large change in length and explore in locations where you couldn't do it otherwise. But if you're just growing in length, it's hard to say, is that exactly a robot? What is your definition of robot? For most people, a robot would be a mechanism that can also autonomously respond based on sensing and reaction to something that's happening in the environment. So we would like the robot to actually steer and change its direction based on things it senses in the environment. And I'll play this to restart the videos. So on the upper left is an entirely autonomous Vine robot that is using a camera that's being pushed forward at the tip in order to seek out light and change its shape in order to achieve a particular configuration. And then some of the other videos here just show other ways in which you can change the shape by pulling on tendons or creating pneumatic tendons. And an important note is that you might have to make a decision about designing a robot that's relatively compact, that has simple actuation such that it can achieve just a particular set of discrete shapes, versus this reversible direction change shown in the videos on the right, where it can say turn left, turn right, and then decide which direction to grow in. So steering is very important to make this eversion principle into something that actually resembles an autonomous robotic activity. So these properties, the growth plus the steering, allows you to do some pretty cool things. You can go through small holes, you can grow under objects in very small areas and then expand radially in order to lift a heavy weight, as shown here. And you can also wrap around things in the environment and even pull on them. And so you can think of it sort of like a very smart rope. It's not exactly a snake because a snake has to push off of the environment in order to move forward. But in this case, the robot is moved forward by internal propulsion, so it actually doesn't rely on contact with the environment in order to do its task. So I'll show a few more videos here of capabilities of Vine robots, and then we'll get into some various applications in different scenarios in which we've used these, and hopefully this will spark your imagination about what soft robots can do for humanity. So on the left, we have some close-ups of going through some difficult surfaces, including a bath of white glue, going through nails that actually poke into it a little bit, to going up a slippery ice wall, and then delivering a sensor through the middle of its body. And this system, which I'll play again on the left, is doing things that it would be almost impossible to imagine any kind of traditional robot being able to do. And because new material is coming from the inside and flipping inside out at the tip, it means that you always have fresh material coming through the tip and you're not dragging any detritus from the environment through it. And on the right, we show concepts that are more related to creating useful structures. This is the example of growing under a crate and then being able to act as a pneumatic jack. I'm going to go back to the beginning again so that we can look at how a robot like this can go under a door and reach a valve and then actually hook onto it, and then you'll see it pull to effectively turn the valve. So it has very limited manipulation capabilities, but if you use the structure in a smart way, you can preform the robot and also pull on it in order to get access and perform some unexpected tasks in scenarios that would keep humans safe and maybe away from a dangerous situation. Let me just also, for the rest of this section of the talk, really highlight robots being used in some interesting scenarios. And the first one I'm going to show here was spearheaded by a former PhD student, Margaret Code, who's on the faculty at Notre Dame. And she took our Vine robot, a special version that she designed, to Peru in order to use it at an archaeological site with a faculty member who was studying the history of Chavin in this region of Peru. And the idea was that there are all of these difficult spaces that are deep underground, which are very difficult to access for people. And there might be some large spaces like the ones shown here, but some of the air ducts and such that can be used in order to examine places that are not reachable normally can be accessed by robots. So there's Professor Code with her Vine robot, which, unlike many robots, has really been now designed to go outdoors, to work in rough environments, and deliver camera and vision into places where you can't normally see. And these are environments where it would be quite dangerous for a human to enter. And so Margaret was able to see things that wouldn't be able to be viewed in any other way. So that's archaeology is a really interesting example, and you can start to imagine the robot going into all sorts of difficult places that humans couldn't go otherwise. And one example that we've done in this vein has been working with conservation biologists and ecologists at Stanford who are interested in studying endangered animals. And in particular, at Stanford, we have a creature called the California tiger salamander. And this is a very cute animal that lives in the burrows that have been abandoned by California ground squirrels, actually. But they are endangered, and depending on the weather and the climate, they can also be a kind of hallmark of how we're doing in terms of protecting our environment. And so this picture shows some of my graduate students actually putting one of these Vine robots into a tiger salamander burrow, going underground in order to inspect and examine these environments. And because the burrows are tortuous in nature and have these complex paths, putting a GoPro on an end of a stick is not the right way to get in there. And there really isn't any other way to non-destructively monitor these environments. So it's interesting, although that project began with an interest in studying the burrows of tiger salamanders, we realized that pipe inspection in general is a really critical task. Throughout the world, we have infrastructure consisting of pipes which provide water, take away sewage and waste, move chemicals around for processing. There's both civil, public, and commercial infrastructure that consists of pipes that in many cases can be very difficult to inspect. And so we've been working hard to make soft robots that are specifically designed to go inside pipes. Often they need very little steering because the pipe itself constrains the robot, but sometimes you have cases where you have a T-junction or you might get stuck otherwise, and so you can have just a tip mount that steers rather than having to steer the whole body of the robot. And this is a project led by my PhD student, Yumeng Chin, and the idea is that we would like to have better, more sustainable infrastructure by providing this non-invasive or minimally invasive access into the pipes, similar to the way in which other types of robots are minimally invasive devices that can go into the human body. And we've even used this type of robot in the tiger salamander burrow. And so one example is as we map the space of a burrow and follow the line, we can do things like measure the temperature here in Celsius as we move around the burrow environment. So it works for pipes that humans make as well as tunnels that animals make. So let's continue along this vein about the importance of being able to do minimally invasive inspection, right? How do we get sensors into locations where you want to keep humans safe and yet still get eyes on what's going on? And one potential application is nuclear facilities, both the types of pipes that I just talked about, but also just in scenarios that might be in open air in 3D that might have, for example, containers of nuclear material that need to be counted and tracked. And so we envision that we can do inspections in hazardous environments by having vine robots that have more three-dimensional capabilities and more steerability. So instead of just the whole thing curving, but that you could curve left and curve right and come up with these snake-like shapes. So in order to do this, we need 3D steerable segments where we can actuate. We need tip mounts with cameras and eventually manipulators. And we need to be able to observe and track things in the environment. And much of the work that we had done until a few years ago, we focused on two-dimensional steering, vine robots that went around the ground or maybe very little bit off of the ground. And we've been able to make those very long. But there are a lot of design limitations in doing this. We didn't have true 3D steering. These materials also had limited lifetime due to leakage, and they're very difficult to fabricate. So we've been focusing recently on three-dimensional steering, and we've come up with a new fabrication method that's also been observed by other research groups around the world, that we can get 3D steering capability and have more efficient fabrication using a technique that I'll highlight in the coming slides. And this work was led by my former postdoc, Zenishbek Zakipov, and my former PhD student, Nathaniel Agaris. So to give you a sense of what it's like to make these vine robots, I showed you a lot of these soft robots, but not really described how you fabricate them. I think this is a nice example of a fabrication technique that really builds on sewing and other methods that already exist in the world. And this is one of the reasons that it could potentially be lower cost to fabricate compared to traditional robots. So we have this unibody design with segments that are embedded into the main body of the robot. And we do this by taking a fabric material, which has a thermoplastic urethane coating on it. And we create basically a sandwich of two of these materials together, and then we seal it along all of the lines that are shown here. So there are two layers, one right on top of each other, and they're sealed together. We create all of these seal lines, which are shown in all the black lines here. And then we fold them and create a seal edge, and then we add some plastic tubing in order to drive it. And to further show some examples of how this is created, we use a Cricut system in order to basically plot onto it some lines that show where it needs to be sealed. And then the welding actually happens using an ultrasonic welding machine that looks a lot like a sewing machine. And these kinds of processes could definitely be automated to be done at scale, but here's an example of my former postdoc Zenit doing this by hand, and you can see it's a lot like sewing, except you're actually using an ultrasonic welder to attach the materials together. So what do you get when you've finished creating a system like this? You have a pneumatic control system with a motorized spool, an air supply, embedded tubing, and then steering actuators that let it move in 3D. And while these systems have the potential to operate autonomously, there are a lot of scenarios where you want to have at least a human in the loop for supervision. So in this case, we had a human in the loop using a game controller in order to steer the robot. So on the left, we see the robot just doing more 2D actions, but let's focus on the video on the right, where we show that the robot can climb up some walls, and you can see actually the video feed in the upper right of the camera. You can see it going up close to inspect the ceiling tiles in my lab, and then turning downwards a little bit in order to see some pile of boxes here in the upper left. In a second. So now it's steering down to look into locations where a person can't easily see, and then it can even spy on some of our design notes on the whiteboard here. So the idea is that these robots can be really used as 3D inspection at a much larger scale than borescopes and some other inspection technologies. And we've even put Vine robots like this many dozens of feet into pipes and place them in environments where there's just no other technology to go. So those were applications that let us become more 3D. But one of the exciting things is having different types of robots paired together to get to even more difficult to reach places. So one of the things that we'd like to do is make the simplest possible robot that can be flown around by a drone. And to do that, we'd like to minimize the amount of actuation on the body of the robot to make it as lightweight as possible. So my student Rihanna Jatosha, who just graduated and is about to start work at Intuitive Surgical, a medical robotics company that I mentioned earlier that made the Da Vinci robot, she did a project which exploited the dynamics of these Vine robots. So you can have relatively lightweight actuators and use a combination of the movement of a drone and reinforcement learning in order to get the robot to do a particular task. So this shows some of Rihanna's early work, where instead of yet putting this Vine robot on a drone, she just showed with a simple sliding actuator that a Vine robot hanging down could be used to reach different targets and be used with reinforcement learning. And what our long-term goal is here is to do inspection and recording of information in difficult to reach spaces. Right? So drones can get close to environments that other types of robots cannot, but a drone can't fly into a very small space, and sometimes with a delicate environment, you don't even want to get the drone that close because it can disrupt things. So the idea behind this graphic is that you have a vine that's growing out of a drone, and that vine could be used to snake into an otherwise inaccessible tunnel or pipe in order to do inspection. And potential applications include inspection under a bridge, Also deploying sensors into the environment, and again, doing this in a way where there's no other type of robot that exists that could actually get in there in order to delicately, say, hang sensors onto a branch for environmental monitoring. So I thought, in the interest of being somewhat pedagogical in this talk, I would say a little bit about reinforcement learning, and this is material from Rihanna Jatosha, and she actually really nicely in her PhD defense discussed the concept of reinforcement learning and how she uses this to control these Vine robots. So these are actually pictures of her family's dog also doing its own reinforcement learning, and I'll use that to guide you through this block diagram. So the idea is you have an agent, in this case her puppy, which is producing an action on the environment. There are rewards for achieving a task. In our case, it's the Vine robot reaching a target, and in the cases on the left, it's a dog actually getting a treat if he learns how to do this task correctly, and observations about the environment. These all come into what's going on in the agent's brain, which is that it has some kind of policy about how to complete a task, and then the reinforcement learning algorithm uses the observations and the rewards in order to update the policy. So in the video on the left, Rihanna's dog is a bit struggling to figure out how do you align these little bones in order to open up the treats, whereas on the right, it's actually figured out how to do this and is able to access some of the treats. And this is exactly what's happening with our Vine robot on the right. The big difference, and this is one of the real challenges in general for robotics and machine learning of any kind, as well as in particular soft robots, because they're so difficult to model, is that and construct and model, is that it would be difficult to do all of the experiments that you would need in order to get the data to do learning. So let me contrast this with other very successful machine learning methods, like for computer vision or recognizing pictures. We have the whole internet's worth of images, for example, cats and dogs, that can be recognized and be used in machine learning algorithms to do that recognition. With robotics, we would need a physical robot to do those tasks. So the point I wanted to make here is that we can create simulations. This video on the lower right is a simulation of our Vine robot, and the reinforcement learning is done on many iterations in simulation. The challenge, though, is you have to make these simulations match the real-world environment as much as possible, otherwise you learn the wrong thing. But there's a huge effort in robotics, and especially in soft robots, because of their complicated mechanics, of understanding the fundamental physics so that you can do learning in virtual environments, in simulation, and use those to learn policies that can be executed in the real world. So that's a little aside tutorial on, in this case, at least reinforcement learning and what's needed for soft robotics. So what Rihanna Jatosha did at the end of her PhD was actually put one of these Vine robots onto a very small drone. I don't have much in the way for relative position, but the drone is only about this big, so it's relatively small, and that means it can't carry much. But if you have a very lightweight Vine robot and a pump to provide the air, you can not only control its position by swinging and adding actuators that curve, but you can exploit the dynamics by having the Vine robot grow and having the drone control system understand how the length of the robot is affecting the dynamics, so that you can do tasks like precisely touch something in the virtual environment. So that was our flying Vine. Now kind of moving back to terrestrial and things that directly interact with humans, let's talk for a minute about patient moving, which is another really critical task. As we have a growing elderly population, a challenge for nurses in homes, as well as for family members that are caregivers. It's very difficult to move an older adult or an injured person from one place to another. So these soft-growing robots can be a way of interacting with the human body. And what we have on the right here are some videos of a soft-growing robot that is now in more of a flat form factor, such that it grows under a person, and then that person can be lifted up using what's known as a Hoyer lift, based on having this sheet that grew under them so that you don't have to turn the patient around. And this is work done in collaboration with Harry Asada's group at MIT, led by PhD students Godson Osele and Kentaro Barheit. So let's end this talk switching away from these mind robots and towards the human connections, the physical connections between people. And I'm going to use this to highlight haptic or touch feedback devices that are based on soft robots. And these devices could be used to create human-human communications for people who are remote, communications between humans and autonomous agents like a directional system, as well as humans and robots in the environment. And when you think about devices that touch or can be touched by humans, we would like them to take on many different shapes and be able to convey useful information. And some of our first soft robots were like the one shown here for haptics, where the human would reach out and touch this object as if it was a digital clay, and we successfully use this for tasks like medical simulation and practice. But now we're very interested in wearable robots. And our first devices weren't exactly soft, but they provided really compelling interactions with virtual environments that could be used for training, as well as for remote communication and design. But these robots were very expensive and they were hard in the sense that they weren't deformable. And so we've been designing fully 3D printed haptic devices out of semi-soft materials, which utilize pneumatics, allowing the pumps and such to be off board and creating a much smaller interface with the human body, and one that is very effective and actually even much more attractive, I think, from a visual point of view. So let's talk about getting these, I'm going to skip over some details here, getting these robots now beyond the fingertips to other parts of the body. We, for years and years, have been focusing on haptic devices for the fingertips, but we'd like to have them mounted in other places to leave the hands free for other tasks. But the challenge is the sensors that are embedded in our skin are much more dense in the fingertips and other parts of the body. And also, we can use active touch with our fingers to explore the environment, whereas in other parts of the body, we need to receive passive touch. So I'll start by saying that we designed some various wearable haptic devices for the arm that were interesting, but ultimately didn't seem to have a lot of practical application. It really took us a while to get to devices that would be much smaller form factor, because the things I'm showing here really aren't going to be something that people will want to wear on their arms every day. So we built on this finger device concept that I showed earlier to put haptic devices in other locations. But the challenge is that if you go out and you touch a virtual object but you get the feedback in a different place, we needed to know, how do you do that mapping? How do you take interactions from the fingertip and put them in other parts of the body? So my PhD student, Jasmine Palmer, did a number of really compelling experiments that showed us what kind of mappings work best. And so this way now, a user can interact with virtual objects, get feedback in other locations of the body, and we can understand how to best do those mappings. I'm going to end with a last example of wearable haptic devices for social touch. So human-machine interaction, or I should say human-human interaction by touch, is a critical part of our mental health and growth. And so when we are apart, or if, for example, in the COVID era, being able to communicate through touch is really critical. And we showed with some traditional motors that you could actually demonstrate very accurately, as people can demonstrate to each other, how someone feels based on touch interactions. So I'm going to end by showing how we're doing this now with a relatively compact wearable sleeve called Haptic, which uses soft actuators that are embedded in knitted material. And a key point is the knit sleeve has to be specially designed and optimized in order to provide a good backing off of which to apply forces to the human body. So you have this challenge where we need to display relatively high forces due to the not so dense tactile sensing in the human skin here, but we also want the overall device to be wearable and comfortable. And that's something we've been able to achieve with knit materials. So hopefully this has taken you on an interesting journey in soft robotics, all the way to soft haptics, ranging from medical applications to a number of applications in the outdoors, all the way to soft robots that allow human-machine interaction. So I want to thank you for your time, and I'm really looking forward to answering some of your questions. Thank you.
Well, thank you very much, Alison, for such presentation. I think we have few members from our audience like really excited, and we got a few first questions, and again, like we would really like to hear from our audience. And if you have any questions, please type them on the AI for Good neural network chat room. So the first question would be, what type of material is used for the Vine robots? Soft enough to compress, yet strong enough to protect against punctures from nails?
Yeah, that's a great question. So there are a lot of material possibilities available. And so some of the properties you need are that it is flexible, but not relatively not stretchable. You need it to be airtight. You need it to also be able to be sealed in some way. And most of the Vine robots we've been making lately to go into outdoor environments that need to be relatively robust, we've been using nylon ripstop. So this is a similar material to what you might find in a windbreaker jacket or even a tent for camping. And then it's not only that one material, nylon ripstop, but usually we get material that's been coated on one side with a thermoplastic urethane, so it has a very thin coating of this meltable material. And that way, when we do ultrasonic welding or even heat welding, those materials can come together. And the garment industry, as well as even the camping industry and such, has many such materials available, and as well as fabrication methods in order to do that. So it's great that in soft robotics, we can often build on fabrication manufacturing techniques and materials that have already been developed and been quite common for other uses.
Well, that's amazing. And I wanted to ask you, like, when it comes to like, what are the criteria, methodologies that you use to determine whether a biological phenomenon can be effectively translated into like one of the functional robotic systems that you are developing?
Yeah, that's a great question. So, in the field of bioinspiration or biomimetics, there are definitely researchers who come at it from the biology side that look at biological systems. They have just curiosity, scientific curiosity and interest about how those biological mechanisms function. And then they may see something that gets translated into a kind of mechanical or robotic application. I think in my lab, we more develop mechanisms and then we see what is used in the biological world that might be similar. And that gives us ideas about how to optimize it or tune it or do it a little bit differently. So I think there are people who are more biologists who directly look at the biology and then invent and design based on that, whereas we are more designing based on mechanical principles, trying to see where they get used in biology and then using that as a kind of optimization and further inspiration.
Okay, no, that's good to know. And I wanted to ask you a question on the Vine robots that of course, we have seen that have many positive and like great applications towards the sustainable development goals.
Yeah.
What are the main challenges that you have in ensuring that they can reliably navigate all these complex, unpredictable environments? And how do you solve these problems?
Yeah, that's a great question. And so I would say at the moment, most of these robots are actually teleoperated. So AI might be used in the design process, or it can be used to determine in advance what sort of capabilities the robot would have. For example, how much it could steer and where it could go. But I think a lot of the what can be used today will be teleoperated by a human operator. And so you exploit the human in the loop in order to make decisions and deal with uncertainty. But of course, that's no guarantee. So I think what we would eventually like to see is that we don't, burden human operators so much with actually driving the robots, and be able to use generative AI and other techniques in order to actually drive the robots. I think because soft robotics is a relatively nascent field, we don't have a lot of complex autonomy yet in these soft robots. But at the same time, because they have many degrees of freedom, if we want to go beyond just controlling the tip of a robot and instead controlling the whole shape, which is sort of too much information for a human to be able to command or even understand, we also will need AI techniques in order to drive these robots. But at the moment, definitely talking to colleagues that do search and rescue robotics, surgeons that do that in medicine, I would say they're very hesitant to immediately assume that AI will solve the problems of dealing with these complex environments. And the path will be a transition from teleoperation by humans to eventual autonomy.
Okay, no, that's very interesting to know. And moving to the soft wearable haptics that you have been like discussing in your presentation, like fingerprint that offer this advanced touch-based feedback. How do we move from the research that you have been doing in this field in the soft wearable haptics uh, to practical consumer adoption? Because this still remains limited. What are the main challenges? Like what is comfort, portability, user experience that we need to close to really ensure this widespread use?
Yeah, that's a great question. There are still a lot of challenges, and it depends on the application. So one challenge is power, right? In cell phones, we have the ability to now provide very simple haptic feedback, vibrations, but that is a very low power haptic application. The vibrations require very little power to create some motion, and then we have sensors embedded in our skin which are primed to react to high frequency information, but the amplitudes can be very low, so that means it doesn't take up that much power. However, if you want to provide more complex signals that are more sort of DC or representing realistic forces in the environment, then you need more powerful actuators. So one challenge is making those small enough. And then the other is how are you going to power those actuators over long periods of time? I do think that pneumatic solutions are becoming more realistic as a possibility. The kind of dirty secret of soft robotics and soft haptics is that in many of the demos you see in papers and videos is they'll be connected to a building compressor, right? And you have a really huge infrastructure, which is not at all mobile. So to make this mobile, we need pneumatic air-based sources that people can take with them. And whether that's pumps, which are currently too noisy and a little bit too big, like noisy just in terms of the sound that you hear, or it is canisters and such, which aren't a super sustainable solution unless you're able to refill them easily. We need to find more ways of providing that pneumatic power, which is nice because it's relatively lightweight, but in a way that is both sustainable and can be mobile in the environment. So I would say actuators and power methods are the biggest two challenges. And I think we have already, because of 3D printing and knitting and other techniques, we kind of understand what sort of form factors we want to have in these devices, but we have to be able to power them.
Yeah, and again, like with the haptic feedback, I mean, this is so important for human-robot interaction. What are the next steps in the field for really enabling, well, like haptic interaction to convey emotions or intent in ways that it's like human-like? What are your insights on this?
Yeah, so let's take, for example, humanoids. Okay, so humanoid robotics is a very popular topic right now.
Yeah.
And much effort is being made towards making autonomous humanoid robots. So let's talk about the different ways in which they could use haptics. So one way is in a human actually training a humanoid robot to do a task, right? So the human has to be able to teach the robot, but in that case, the human and the robot need to get the same sort of touch feedback. So you could imagine a human sitting at a training console, moving some fancy joysticks, or maybe just moving their hands in air, and then being able to have a humanoid robot imitate those behaviors, and the humanoid could learn from that. So that's a learning from demonstration by teleoperating the robot. And the human would need haptic feedback for that. Another aspect of haptics, which is not so much about haptic feedback to a human operator, but just the robots themselves using the sense of touch, is really important. So if you have a humanoid robot, or really any robot that is maybe, helping lift up a patient, like the example I showed earlier, which was a very simple example of that, but let's say you want to actually have a humanoid lift up a patient and move them, it needs to be covered with sensors that can actually modulate that interaction. And so I talked about haptic feedback in terms of receiving haptics on the human side, but we need better haptic or tactile sensors on the robot bodies that are also, they're accurate and also themselves sort of soft. So you have that soft interaction with the human body. That also needs to be worked on quite a bit. There's a lot of work out there in tactile sensing, but many of those tactile sensors require many, many wires, and it's difficult to lay them out over a large area of a robot body.
Oh, that's amazing. So, yeah, I think we're going to have a lot of these insights as well moving towards our AI for Global Summit in Geneva in July on tactile sensing, tactile feedback, and so on. I would like to ask you one last question, Alison, because I think we're running out of time now. How do you envision what is the future of this field in the next 5-10 years? Like any breakthroughs like coming up soon? What are the main challenges right now for you?
Yeah, I'd say some of the big breakthroughs that will be coming are new techniques in 3D printing that enable a lot more access to different materials being placed in different ways for fully functional soft robots. That's one. And another will be really seeing soft robots moving away from research labs and into, or they will probably still stay in research labs, but really moving into applications that benefit humanity. I think up until now, there have been a lot of really cool scientific results, but it's sort of time for a reckoning. These robots have to show that they're actually useful in the real world, and we'll see that soon, I think.
Well, I think that we're very much looking forward to seeing that and using these robots in everyday life. So now I would really like to thank you, Alison, for your time, and again, like for all the attendees for such an interesting session. And again, we encourage you to check out the AI for Good program online to see more robotic sessions that may be of interest to you. And this is the end of the AI for Good event. And now I would like to give the floor back to Anna for the closing information. Thank you very much again. Thank you.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the e-shop, and build your personalized AI for Good program. Let's shape the future of AI for Good.